Okay, so we're going to do another example of integration by method of partial fractions. And in this example, we have a couple of linear factors at the denominator, x, and 2x plus 1. But 2x plus 1 is raised to the third power, so that shows up as order 3 factor. So we're going to do what we discussed in class yesterday for this particular example. So let's change the color here. The goal here is to write our fraction as a sum of simpler rational functions. Oh, before I go on though, let's just point out that this is in fact a proper function, because the degree of the numerator is 0 and the degree of the denominator is going to be 4, which is clearly bigger than 0. So we don't have to worry about making it proper. And we want to write this as a sum of, something over x plus, now how do we deal with that 2x plus 1 to the third power? Well, in general, that's going to be a cubic polynomial, right? But we found out in class that it's easier to deal with it by spreading out. So if it was cubic, we would have to have a quadratic in the numerator to be most general. But we found out in class that it was easier to spread it out into a couple different fractions, that in general, we're always going to be able to spread it out into fractions whose denominators look like that thing raised to the various power up to 3. So now the numerator is going to be, well, the most general numerator that allows us to keep this as a proper fraction. So for the x, that's degree 1. That's going to be an a, just some constant. And for the 2x plus 1, again, degree 1, so it's just going to be some constant. But as we noted, we're actually using the 2x plus 1 as the thing that's the maximal degree here. So in each of these, we're going to have a constant. Now let me just point out, if I add these together, I'm going to get a polynomial with a 2x plus 1 cubed in the denominator, whose numerator is going to be a second degree polynomial, and it's going to be as general as can be. So this, in fact, is the general way to write that. It's just the convenient way to write it general. So, of course, then we're going to set these equal, and in particular, we're going to set the numerators equal when we add the fractions. So when I add the right-hand side, the numerator is going to look like a times 2x plus 1 cubed, right? The common denominator is going to be x times 2x plus 1 cubed, plus bx times 2x plus 1 squared, plus cx times 2x plus 1 plus dx. And of course, that's got to equal 1, and that has to equal the numerator of the left-hand side for all x. Even though the fractions aren't defined at x equals 0 and x equals -1/2, two polynomials are can't differ at just a couple of x's. So those are going to be equal for all x, and we're going to use that fact. So we'll plug in different values of x. So we'll try x equals. So we've got now, let me just point out what we have here. We have 4 unknowns, a, b, c, and d. So we need to solve for those 4 unknowns. So we need 4 different equations. So we're going to choose x values to plug into this expression right here to allow us to get 4 different equations. We're going to need 4 different x values, and we'll choose them as wisely as we need to make simple equations. And of course, x equals 0 looks like a good thing to try. I'm going to try x equals 0 here. And then on the left-hand side, of course, that's always going to be 1. On the right-hand side, we're going to get 2 times 0 plus 1 cubed, that's 1, so I'm going to get a. And everything else zeroes out. So if you notice here, all of these are multiplied by x, right? So that's all zeroed out. So we can just ignore that, and we get a equals 1. Okay, so let's do a different color here. And we're going to replace that a with a 1 now. Okay, so, okay. Now, what else can we try? Let's try x equals minus a half, because that zeroes out a whole bunch of other terms. So if I try x equals minus a half, I'm going to get 1 is equal to, well, these terms, let's just point out here, these terms here all zero out, and I just get minus a half times d. That is d equals minus 2. Oops. So I get a equal 1, d equal 2, and so I can write that d as a 2 now, right? Okay, and notice there's nothing else we can plug in to zero out everything, so we're just going to plug in some simple points. So let's just try x equals 1, right? So if I try x equals 1, I'm going to get 1 is equal to 2 plus 1 cubed, that's 3 cubed, that's 27, plus 3 squared, 9 times 1, so that's 9b, right? Plus 3c plus 6. And let's simplify that equation a little bit. Subtracting 27, I'm going to get minus 26, so that's minus 26. Minus 6 is minus 32, right? Is, yeah, 27, 32 is equal to 9b plus 3c. Okay, notice I can't solve for b or c with that. I'm going to need another equation. So let's try x equals minus 1. Another simple thing. So I get 1 is equal to. So x equals minus 1. I'm going to have minus 2 plus 1, that's 1 cubed, so that's minus 1, minus b times minus 1 squared times minus, okay, so I'm just going to get minus 1 minus b, and minus c times minus 1, that's going to be plus c, and 2 times minus 1 is minus 2. So that simplifies to what equation? That simplifies to it looks like 4 equals minus b plus c. Okay, so if you notice now we have these two equations that we can use to solve for b and c with. So let's scroll down, give us a little bit more room here. Okay, so if you remember, how do you solve for equations? Well, one thing you could do is you could solve for c and plug in, or you can add equations. I think what I'm going to do, let's call this E1, and let's call this E2. So I'm going to take, let's say E1 minus, let's line these up, minus 32 equals 9b plus 3c, and I'm going to multiply the bottom by 9, and I get 36 is equal to minus 9b plus 9c. And I can use this to solve for c, right? Because now if I add those two, I lose my b. So 36 minus 32 is 4, right? Is equal to 9 plus 3, which is 12c. So it looks to me like c is equal to a third. And now, using c equals to a third, let's take this. If c is equal to a third, that's 4 equals minus b plus a third. So b is equal to 1/3 minus 4, which is equal to minus, what is that, 12 thirds, 11 thirds, is that it? And there we have it, b is equal to minus 11 thirds. Okay, so now, let's go back up here and rewrite that. So this is equal to a is 1, so the integral of dx over x, and b is, what do we have b? b, it was minus 11 thirds, so we get minus 11 thirds integral of dx over 2x plus 1, and c is 1/3, so we get plus 1/3 integral of dx over 2x plus 1 squared, and finally d is minus 2, so minus 2 integral dx over 2x plus 1 cubed. So let's get rid of what we have down there below so we have more room to work. Okay, so these are actually very doable integrals. This is going to be, of course, that first one is just what? It is just ln of absolute value x. I don't even need to use substitution there, or don't even need to consider a u substitution. Now the second one is, it's a lot like the first one. It's a little bit further, right? You could do a u substitution in for that. Again, we could do u equal 2x plus 1, right? Then, of course, 1/2 du is equal to dx. But like I mentioned before, when you have just a linear factor that's your u, you should try to get used to being able to do that in your head. It's going to be ln of that thing. And, of course, when I take the derivative of 2x plus 1, that's 2, and I need something to counter that, and so I need 1/2. So I need times 1/2. Now, this other one is actually 2x plus 1 to the negative 2, right? That's just a power function when I do the u substitution, u equal 2x plus 1. So I just get here plus 1/3 times 2x plus 1 to the negative 1, right? Negative 2 plus 1 divided by negative 1. And of course, I need that times 1/2 there to counter that 2. And the same thing's going to happen over here. I'm going to get a 2x plus 1 to the negative 2. Negative 3 plus 1 is negative 2 divided by negative 2. And then I need that times 1/2 again. And of course, I got the plus c. So let's just simplify that, and we're done. ln of x minus 11/6 ln of 2x plus 1 minus 1/6, or 1/6 times 2x plus 1. The 2's cancel. Let's see, I get a plus 1/2. 2x plus 1 squared. And there we have it. I do that.